In earlier lectures, we saw the nonlinear effect coming from the chi3 nonlinearity. In that, of course, we considered only one signal propagating inside the optical fiber, and then we saw that the refractive index depends upon the mod of the electric field square, that is the power density inside the optical fiber. Today, we are going to see the same third order susceptibility if we take, and if you do not have only one signal propagating inside the optical fiber, if you have multiple signals propagating simultaneously, then what kind of interaction takes place between different signals. So, in this lecture, we are going to discuss two phenomena. One, what is called the cross phase modulation, and second one is what is called 4-wave mixing. Both these phenomena are related to the term which is due to third order susceptibility. So, let us look at this phenomena of what is called the cross phase modulation. So, let us say we have the electric field which has two frequency components. So, the electric field there are two frequencies with amplitude, let us say E1 and a frequency omega 1, and there is another signal with amplitude E2 and a frequency omega 2. Then if we substitute this into the polarization expression, we will get the nonlinear polarization created inside the material that will have various components now. So, it will have a component, nonlinear component at omega 1 e to the power j omega 1 t. It will have a component at frequency omega 2 e to the power j omega 2 t, plus it will have other terms which lie in the same frequency range, and that is if we consider a frequency, let us say 2 times omega 1 minus omega 2 or 2 times omega 2 minus omega 1, these are the terms which will be approximately in the same frequency band. So, you will have terms like 2 omega 1 minus omega 2 with a frequency 2 omega 1 minus omega 2 plus similar term with 2 omega 1 and so on. And this nonlinear polarization which we get, this at frequencies omega 1 will be related to this chi3 nonlinearity, and the term mod E1 square plus 2 times mod E2 square E1. Similarly, we can get the nonlinearity at frequency omega 2, that is this chi3 2 times mod E1 square plus E2 square E2. And then because of this nonlinearity, the change in refractive index delta n at jth frequency, where j could be 1 or 2, that is given by this nonlinear coefficient n2 times mod of E j square plus 2 times E 3 minus j square. Now, note here that when we had only one frequency, that means let us say the E2 was equal to 0, in this only one frequency is propagating, that time this quantity will be equal to 0, and then we get the change in refractive index, which is the nonlinear coefficient, and 2 times this E1 square. That is the case which is the Kerr nonlinearity analysis which you have done when we derived the nonlinear Schrodinger equation, considering only this term. What we are seeing now, that when the other signal is also present here, the change in refractive index is going to be because of the signal itself, plus there will be contribution coming from another signal which is coexisting along with this signal. But the most important thing to note here is that the change in refractive index due to this signal propagation has an enhancement factor of 2 compared to this signal. And that is a very interesting thing to note. What that means is that the nonlinear effect of another signal is twice stronger compared to the signal itself. And as we have seen earlier, when the signal propagates inside the optical fiber, this change in refractive index gives me a phenomena what is called the self phase modulation. What we are saying now is that since the refractive index change is going to take place because of this frequency, another signal which is this signal, the change in phase is not only due to because of the signal itself, but it is also due to another signal which is propagating. So, as we had a phenomena earlier when this was not present, that phenomena we called the self phase modulation, because the signal phase used to get modified by itself. Now, we are saying that the phase is going to get modified by itself plus another signal which is coexisting. That phenomena now then is called the cross phase modulation. So, it is possible that if this signal is very weak compared to this signal, the contribution coming because of this term is negligibly small, but this contribution could be very strong because this intensity of the signal is much larger. So, due to the third order nonlinear susceptibility, we see this phenomena what is called the cross phase modulation. And when you are having a phenomena like this, then one can say that the phase change, the nonlinear phase change, as we saw in terms of the self phase modulation, can be given as delta and j times z. So, here j could be 1 or 2, 1 or 2. So, if I put j equal to 1, this is E1 square plus 2 times 3 minus 1, which is E2 square, and if I put j equal to 2, this will be E2 square plus 2 times E1 square. So, this phenomena is what is called the cross phase modulation. So, we have this phenomena what is called cross phase modulation, and in short it is called XPM. So, whenever we are going to have multiple channel transmission inside the optical fiber, there would be this phenomena of cross phase modulation. Now, as we know that for a WDM system, when large number of channels propagate, if there is sufficient power in each channel, then there would be change in the phase of each signal because of the presence of another signal. Also note here that when you are having a large number of channels transmitting, let us say n channels are transmitting, then each channel will be affected by the power present in remaining n minus 1 channels. And since the effect of each of these channel is going to be 2 times stronger compared to the individual, so you see the collective phenomena of self phase modulation, cross phase modulation is much stronger compared to what you would see in the self phase modulation. So, one can then say that if you wanted to formulate a problem, essentially we require the same nonlinear Schrodinger equation looking into the effect of the cross phase modulation. So, as we did earlier also, we can do the formulation similar way. We say that the field distribution for the JH channel that is having a transfer function field distribution, which is in the x y, which is the transfer plane for the fiber, an envelope function which is going to evolve as a function of z, and a phase constant which is minus j beta 0, but now this beta is going to be a function of the frequency. So, this is for the JH channel times z. So, if you do the same steps what we have done for the self phase modulation, we again would get two equation, one would govern this field distribution and other one will give the evolution of the envelope as a function of distance on the optical fiber. So, following the same steps what you have done earlier, one would then get the nonlinear Schrodinger equation that can be written as a j divided by dz plus beta 1 j d a j by dt plus minus j beta 2 j by 2 d 2 a j by dt square plus alpha j, which is the attenuation term, by 2 a j is equal to minus j n 2 omega j by c, and the nonlinear terms which are proportional to the mod of a square. But since now the other channels are also present here along with this, you will get contribution from other channels also. So, let us say along with the JH channel, even the KH channel is present. So, you will get here called FII mod let us make j square plus the cross phase modulation term 2 times f j k mod a k whole square. So, as we have seen earlier in the nonlinear Schrodinger equation, this is the change rate of change as a function of distance. This term gives me the group velocity, this term gives the group velocity dispersion, this term gives the attenuation, and this term gives the nonlinearity. And if you recall, earlier we used to have a term which is simply mod a square times a j. So, there has to be a j here. So, it used to have a term which is simply mod a j square multiplied by a j. However, now what we are seeing is we are having an additional factor here which is this f j j or f j k, and this quantity is what is called the overlap integral. So, since there are multiple signals propagating, how much overlap of the field takes place between two signals? That is captured by this quantity, what is called an overlap integral. So, the overlap integral is defined as f j k, that is defined as over the cross section mod of f j x y square f k x y square dx dy divided by integral mod of f j x y square dx dy multiplied by integral mod of f k x y square dx dy. So, when you are having same quantity here j is equal to k, that time this quantity essentially will reduce to the effective area. So, you will see that this quantity will be for j equal to k, that only one signal is propagating, that time this quantity will be 1 upon A effective. That is what we got for the single signal propagation on the optical fiber. However, when we are going to have the multiple signals propagating, what this factor captures is, it sort of shows you how well the two fields are completely overlapping each other. But as we know that this field distribution is going to be a function of frequency. So, if you take widely different frequencies, then the two fields will not have a good overlap, and then this quantity will essentially reduce, or the interaction between the two channels will reduce. So, this term essentially is capturing how effective the interaction between these two channels are going to take place. Having done this, then the same equation now can be written in terms of that nonlinear parameters and so on, as we had done earlier. So, the equation will become A dA1 by dz plus this quantity is beta 1 for the jth equation. Let us say we are writing for channel 1. So, we know that this quantity will be 1 upon group velocity for channel 1. So, this is 1 upon Vg1 dA1 by dt minus j, you have beta 2, and for channel 1 by 2 d2 A1 by dt square plus alpha 1 by 2 A1 is equal to minus gamma 1 mod A1 square plus 2 times mod A2 square A1. And same thing you will have, same equation you will have with for A2 also. If I replace here A2 A1 by A2, then I will get a equation, similar equation for second signal also, where this quantity gamma, as we have defined in the earlier case, this gamma is equal to this N2 nonlinearity coefficient j, so is omega 1 divided by C times A effective. So, if the two frequencies which I am considering are very close to each other, then this quantity will be 1 upon A effective practically for both the things. So, the parameter which we have defined here, which is FJJ, which is F11 or F12, these two are equal, and that is almost equal to 1 upon that A effective which we have defined for the fiber. So, you see in the case of XPM, the nonlinear Schrodinger equation has, in addition to the original term which was this, one more term which is coming because of this, and depending upon the amplitude of A1 and A2, this term may dominate or this term may dominate. So, one can then ask a question, if you are having this phenomena, what will happen when the signal start propagating inside this? So, few things to note here. First of all, when two channels start propagating, earlier what we had done is, we had taken this term here and we had defined a moving frame, so that this term vanished, because we have got a frame which was moving with the pulse. So, in that frame of reference, then this velocity was equal to 0. But now, since we are having two signals traveling, you cannot define now a frame of reference which can be synchronized with both of them. So, essentially this term will always remain, or even if you try to move a frame with one signal, the another frame will be moving with a difference of the two velocities. So, this term will in general will always remain with that. So, now the phenomena is as follows. Imagine a situation that you are having a pulse and there is another pulse which is traveling, but these two pulses are not traveling with the same speed, they are traveling with different velocity. When they travel with different velocity, they essentially slide through each other as they propagate. So, if you take these two pulses, when they overlap, the interaction between these two take place and the cross phase modulation phenomena can be seen. When they slide through each other and they cross this, then the self phase phenomena vanishes, because now these two pulses are not interacting with each other. This is what is called a walk off phenomena. So, this will be related to the difference in the two group velocities. So, if you consider a fiber where the group velocity is practically constant, then you will have a strong interaction taking place between these pulses. But if you consider the channels which are widely separated, then these two will travel with different velocity, and only whenever there is an overlap between the two, the nonlinear interaction will take place, otherwise the interaction will not be there. So, the phenomena which we have seen earlier for the self phase modulation, the similar kind of behavior we will expect in this situation also. Only thing is, in this situation, the nonlinear phase will be affected by the additional channels also. So, if we want to this phenomena to be weak, then we should create a situation so that the pulses do not travel together for a long time. That means, we should create a fiber which have a large group velocity change as a function of frequency. That is saying that we have a large dispersion on the optical fiber. So, if you consider a fiber where the dispersion is large, then there will be significant difference between the velocity of the two signals, and then the walk off time will be very short. So, the nonlinear interaction between these two pulses will be very small. On the other hand, if we want to make use of this phenomena of cross phase modulation, then we should use a fiber which is more like a dispersion flattened fiber, so that all the signals travel with more or less same velocity. So, the walk off time is much longer and there would be strong interaction between the different signals. So, if we use now a fiber which is a dispersion flattened fiber in a WDM channel, you will see that the effect of cross phase modulation will be much more. So, to avoid the cross phase modulation effects in the WDM signal, it is desirable to keep some dispersion into the system, because if the dispersion was made 0, then different frequencies would travel with same velocity. If they travel with same velocity, then they will interact more and there will be more effect of cross phase modulation of the signal. And as I already mentioned that in a WDM system where the number of channels are very large, every channel is going to be affected by all the rest of the channels. So, if you consider let us say 128 channel WDM system, every channel will have the effect due to remaining 127 channels, and each one, even if it carry power of the order of about 2-3 milliwatts, the total power with 127 channels would be easily of the order of about 500 milliwatts. And then the nonlinear phase which will be created because of this will be significant. So, in a WDM system, one will see that the cross phase modulation effects would probably be much stronger compared to the self phase modulation, because each channel is going to carry still a power which is very small, few milliwatts, and at that power the self phase modulation will be very weak, but collectively the cross phase modulation would really have a strong effect. So, it means that in a WDM system, if we want that the channel should not get affected by the neighboring channels because of this phenomena, then one should use the fiber which has dispersion. So, now you see, originally when we talked about the optical communication, we wanted to make the dispersion small, so that the pulse broadening does not take place. Now, when we are talking about WDM channel and when we start looking into these additional effects, we find that making dispersion 0 over very wide wavelength range is not a very good option, because in that situation these different channels will start interacting and they will create some kind of crosstalk between different channels. So, XPM affect the signals in different frequencies. It also gives you the same phenomena like the spectral broadening as we saw in the self phase modulation. Only thing is, in this case the spectral broadening is not symmetric around its original frequency as was happening in the self phase modulation. You may get asymmetric spectrum developed because of this phenomena of cross phase modulation. So, this is one of the important aspect of the same third order susceptibility which was giving you the propagation, self phase modulation and solitons and so on. When you are having a multi-channel transmission, the same third order susceptibility gives you this phenomena of crosstalk due to nonlinear effects. The same phenomena, when I look at it, gives you one more effect, and that is what is called the four-wave mixing phenomena. Now, what is the four-wave mixing phenomena? This phenomena, if I compare with an electronic system, this phenomena is identical to what we used to say as the interchannel mixing or intermodulation products. So, we know in an amplifier, when amplifier goes into saturation, if you put two frequencies inside the amplifier, the third frequency is generated. Because of the nonlinearity, these two frequencies, they give the products which are sum and difference products and so on. Exactly same phenomena we see in the optical fibers also, because of this third order nonlinear susceptibility. So, we are saying that if you consider now a nonlinear polarization, which you have seen is third order susceptibility, and let us say now I am putting 3 signals. So, I have 3 frequencies simultaneously put inside the optical fiber. So, they will interact through this term, and then because of this intermodulation they will produce the frequency, force frequency, which will be sum and difference frequency of the 3 signals. So, they will produce frequencies which is omega 1 plus minus omega 2 plus minus omega 3, and they will be having the wave numbers which is k 1 plus minus k 2 plus minus k 3. So, when 3 frequencies go inside the material because of the nonlinear nature of the material, you will see there are additional frequencies which would get generated in addition to the original frequencies which were omega 1, omega 2, omega 3. So, if I just take all possible combinations, you will see originally we had 3 frequencies omega 1, omega 2, omega 3, but now we are going to generate frequencies which is omega 1 plus omega 2 minus omega 3, omega 1 plus omega 3 minus omega 2, omega 3 plus omega 2 minus omega 1, 2 times omega 1 minus omega 2, 2 times omega 1 minus omega 3, two times omega 2 minus omega 1, 2 times omega 2 minus omega 3, 2 times omega 3 minus omega 1, 2 times omega 3 minus omega 2. So, you remember when we were talking about this term of non-linearity here, we have said these are the different frequencies which are going to get generated, and we are going to look at only those frequencies which lie in the same frequency band. So, you see here that we had original frequencies which were omega 1, omega 2, omega 3, let us say they lie in the same band. You see all these quantities, all these frequencies, they have the same range. So, this term has a frequency almost comparable to this one has almost comparable to this, right, and so on. We may have frequency where omega 1 plus omega 2 plus omega 3, but this frequency will be approximately 3 times omega 1. So, that will lie in totally different frequency band. So, this combination is going to create many more frequencies, but those frequencies which are double of any of these frequencies or 3 times, we are not looking into, because they are going to be different frequency band and very easily they can be eliminated by filtering process or whatever it is. But these frequencies, they all lie in the same frequency band. So, essentially what we are saying is now that when different signals propagate, because of this nonlinear process, the sum and different frequencies are created, and these new frequencies are going to lie in the same frequency band. That is the phenomena what is called the 4-wave mixing. And this phenomena electronically, if you see, this phenomena is also what is called the intermodulation phenomena. So, from the electronic communication terminology, this phenomena is exactly identical to what you see inside the amplifier, and these frequencies are what are called the intermodulation products. In optical communication, this phenomena is what is called the 4-wave mixing. So, now you see that this phenomena of 4-wave mixing, which is coming because of that term which is the XPM kind of term, this may affect the propagation of a WDM signal. So, let us consider a simple WDM system where there are 3 channels, and as we know in WDM the wavelengths are equispaced. So, let us say we have 3 channels. Let us say this is a channel here which is at omega 1. Let us say I have a channel here which is, let us say, omega 2, and I have a channel here which is omega 3. So, this is a WDM system, and here the delta omega is same for all these frequencies. So, this is also delta omega, this is channel separation, this is also delta omega, the channel separation, and so on. Because in WDM system the channels are equispaced. Now, let us say these 2 frequencies when they start propagating. So, this frequency now omega 2 is nothing but omega 1 plus 2 times delta omega, and this frequency omega 3 is omega 1 plus delta omega. And as we have seen earlier, now the frequencies which are going to be produced will be combination like this. So, omega 1 plus omega 2 minus omega 3 and so on. One can now look at what kind of frequencies can be generated by these 2. So, I will get the 4th frequency omega 4, which is omega 1 minus plus omega 2 minus omega 3. So, if I make omega 1 plus omega 2 minus omega 3, that will be equal to omega 1 plus omega 1 plus 2 times delta omega 2 minus omega 3, which is this. So, minus omega 1 minus delta omega. So, this is equal to omega will cancel, 1 delta omega will cancel. So, this is omega 1 plus delta omega, which is same as omega 3. So, this is same as omega 3. So, now this phenomena, look at it this. When these 2 frequencies omega 1 and omega 2 starts propagating, they have a tendency to now generate a frequency which is omega 3. And omega 3 frequency is the frequency corresponding to another WDM channel. But what this means is that means by this nonlinear process, these 2 channels are going to put the power into this channel. Or you will see that there is going to be some crosstalk created between this channel and this channel, and similarly between this channel and this channel. Now, this we have seen only for the 3 channels. When you are having large number of channels propagating, each of this channel here would have a tendency to get the power from this to this and this to this. Or in other words, there is going to be a crosstalk created between all the WDM channels. So, you have a phenomena what is called crosstalk between the WDM channels. What is the solution to this? If you want to avoid this phenomena, because when we are looking at this phenomena, it becomes very clear that when large number of channels are going to propagate, because of this nonlinearity, the power is going to flow from one channel to another channel, and that will create some kind of crosstalk. So, to avoid this phenomena, then it looks that we should not transmit the channels which are equispaced, because this phenomena can easily be avoided if this frequency which is generated here omega 4, if it does not lie on this frequency here, then there is no question of getting the power into this channel from these two. So, if the nonlinear effects are present, then one of the solution would be that we should put the channels such that they do not lie on this grid, so that the power from one channel to another channel cannot flow because of this kind of relations here. So, the equispaced channels from the nonlinearity point of view probably is undesirable thing, because that creates more crosstalk because of the four-wave mixing phenomena. So, now we see that if you want to reduce the effect of the cross phase modulation and the interaction between different channels, we should not create channels between which are equispaced. But one more thing which can be done, and that is again when the interaction between these things take place here, it depends upon how these channels are traveling with each other. So, again the efficiency of this four-wave mixing depends upon what is called this interaction factor or the walk off between different channels. So, again if the signals were traveling together, different frequencies were traveling together, they will have a strong interaction and they will create more crosstalk. But if they were not traveling together, then this phenomena will not be a very efficient phenomena. So, again it boils down to the same thing, that we should increase the dispersion on the optical fiber, so that even this four-wave mixing phenomena becomes weak and the crosstalk into the system is reduced. So, it looks like that originally when we were considering a single channel kind of transmission, minimization of dispersion on optical fibers seemed to be more desirable. But now considering all these advanced effects which we see, it looks that making dispersion 0 on optical fiber is not really a good option. Probably we should keep some dispersion on optical fiber, so that these effects do not build up and their interaction and their effect on the signal propagation can be minimized. So, in modern high speed communication, the requirement would be to not to make the dispersion 0, but to keep some residual dispersion, and by doing that this nonlinear effect can be reduced in a multi-channel transmission. But the same four-wave mixing phenomena now can be used for something to achieve. For example, when we are talking about a wavelength rooted network, and if you wanted to create sort of a non-blocking situation, many times we require conversion of wavelength, so that a wavelength which is not present into the next channel, the another wavelength can be transmitted. So, imagine a situation that you wanted to send some multiple wavelengths which are going on the network, and a lambda 1 can be transmitted up to certain distance, but for the next path lambda 1 is not available because the lambda 1 was already allotted to somebody else. So, one possibility is that that particular transmission is blocked, that means that communication channel, the optical path is not available. Or other possibility is, if you have a wavelength conversion, transfer the data from one wavelength to another wavelength and then the path is open. So, a wavelength conversion may increase the throughput inside an optical network if the wavelength conversion is there inside the optical network. Now, this phenomena of four-wave mixing can be used for changing the frequency of a signal. So, imagine a situation that if I have some device in which some frequency comes in and I put another frequency, this is some frequency of 1, this is some frequency of 2. And then at the output, I may get a frequency which is 2 times f1 minus f2 or 2 times f2 minus f1. So, if I can choose this frequency f2 in such a way that any of these two frequency matches with the frequency in which you are interested in for the next path, the signal data which is riding on this frequency essentially can get transferred to another frequency, this f3 frequency. So, this phenomena can be used for the frequency conversion. So, 4-wave mixing phenomena, if you really look at just for from the interaction point of view, yes, it may create crosstalk between different channels, but the same phenomena when used more intelligently, this can be used as the frequency converter, which is used for wavelength routed networks for creating non-blocking systems. So, like that you have sort of a various system considerations when nonlinear effects are present. So, let me summarize what we have done actually in this. We have simply started with the nonlinear effects, saying that if the light intensity is large, then the polarization does not have only the linear term, which is the chi1 term, but we also get contribution due to the higher order susceptibilities. Then we saw that for a molecule like glass, the second order susceptibility contribution is negligible. So, most of the contribution which you get, nonlinear contribution, that is due to the third order susceptibility, which is chi3. Then we saw that for that nonlinear contribution, if the signal propagates, we have a phenomena what is called the self phase modulation. And then we saw that the self phase modulation, when combined together with the dispersion, the group velocity dispersion, you get a phenomena what is called the soliton. Then we saw that the same third order susceptibility, when multiple signals propagate, the signal get affected by the other co-propagating signals. The phase, as was happening in the self phase modulation case, now the phase of a signal gets modified by the neighboring signal, and that phenomena then is what is called the cross phase modulation. The same phenomena also creates new frequencies, and that phenomena we saw is what is called the 4-wave mixing phenomena. And then we saw that the 4-wave mixing phenomena actually creates crosstalk between the neighboring channels, and its effects can be neglected or sort of reduced by using the fiber which are having some dispersion, so that these signals can keep walking through each other, and because of this the efficiency of nonlinear interaction weakens. To avoid the cross phase modulation as well as the 4-wave mixing phenomena, probably it is wiser to use the fibers which have some dispersion and not a zero dispersion fiber. Then at the end we also saw that the same 4-wave mixing phenomena can be used for creating new frequencies or for the frequency conversion, which is required for wavelength routed network for creating non-blocking situations. So, in last couple of lectures, essentially what we have seen is that inside the optical fiber, we see a variety of nonlinear phenomena. In fact, optical fiber is a very good laboratory of nonlinear effects, because we saw in the very first lecture of nonlinear optics that the nonlinear effects inside the optical fibers get enhanced by almost a factor of billion. So, with very little power, the nonlinear effects can be easily observed inside the optical fiber. So, we have seen just a cursory look at the nonlinear effect which take inside the optical fiber, and many of the effects are now used wisely to improve the quality of the signal or to getting certain functionalities on the optical fiber network. So, that concludes our discussion on the nonlinear effects on optical fiber. The discussion was no way exhaustive. So, if one is interested in having more in-depth understanding, there are a wide range of books available, where one can develop in-depth understanding on each of the topic which we discussed. But through these lectures, a flavor has been provided that what kind of nonlinear effects can exist on optical fiber and how they can be wisely utilized for improving the transmission capacity and the quality of data on the optical communication channels.